Somewhere in the darkness of the universe, a star dies, and it explodes twice. At first, it bursts like a supernova, a dazzling flash, brighter than an entire galaxy, brighter than billions of suns combined. And then two neutron monsters are born from its ashes and begin to circle around each other, getting closer, faster and faster, until they collide and create a second explosion. Kilonova. Until this year, no telescope on Earth, no team of scientists had seen these two events in the same system. It was the astrophysical grail, a theory that came together nicely on paper, but was never given to observers. And in the spring of this year, the space monster made itself felt. The gravitational wave detectors were the first to flinch, catching ripples in the very fabric of space-time. Behind it is a monstrous gamma-ray flash. Behind it is an optical afterglow. And when these data came to astrophysicists around the world, silence reigned in the laboratories. The same silence that happens only when you see something so incredible that the brain just refuses to accept it. Because this should not have happened. To understand why, you need to understand how stars die in general. To really figure it out. Because this is not just a beautiful picture with an explosion. This is one of the most cruel and at the same time the most productive processes in the universe. A star is war. A long, incessant war between two forces. On the one hand, gravity. Merciless, eternal, she presses on the star from all sides and wants only one thing, to squeeze it to a point. On the other hand, there is thermonuclear fusion in the nucleus. An explosive combustion that produces such a flow of energy that it literally bursts the star from the inside and does not allow gravity to win. As long as the fuel is burning, gravity loses. The star shines for billions of years. Step by step, it synthesizes heavier and heavier elements. Hydrogen into helium, helium into carbon, then neon, oxygen, silicon, and finally, iron. And this is where gravity gets its chance. Iron is a chemical dead end. Iron synthesis does not release energy, it absorbs it. As soon as the core of the star becomes iron, the burning stops. The pressure drops. And gravity, which has been waiting for this moment for billions of years, wins instantly. A core the size of the Earth shrinks to the size of a city in 1 second. The density becomes so monstrous that 1 teaspoon of this substance would weigh as much as Mount Everest. And the entire outer shell of the star, hundreds of solar masses of gas, falls on this suddenly solidified core and bounces off. The shock wave tears the star apart from the inside. This is a supernova. The iron atoms in your blood were once in the core of a dead star. The calcium atoms in your bones were synthesized in the bowels of a star that exploded billions of years ago. We are literally stardust. This is not a metaphor. This is chemistry. But here's the catch, supernovae, for all their power, can't create everything. There are elements for the synthesis of which an ordinary supernova explosion is simply weak. Gold, platinum, iridium, thorium. To create them, you need conditions so prohibitive in terms of neutron density, so monstrous in temperature, that nature had to come up with something worse than a supernova. kilonova. This event occurs when two neutron quarks of stars, two objects so dense that the very spacetime around them is distorted, find each other. They circle in a deadly dance, getting closer with each turn, losing energy through gravitational waves, ripples in the very fabric of spacetime. The rapprochement lasts for millions of years, then thousands, then years, then seconds. And when they collide, something happens for which we hardly have enough words. The temperature reaches values at which the very concept loses its meaning. Neutrons overwhelm the nuclei of atoms, building elements that do not arise anywhere else in nature. This process, fast neutron capture, the R process, produces gold. Literally. Each gold ring on your finger was synthesized in the collision of two neutron stars somewhere in another galaxy billions of years ago. It flew into space, became part of the planet, and ended up on your hand. Kylan scientists observed neutron stars too. Supernovae, thousands of times, but always separately. Like disparate pages of one book, which did not add up to a single story. Because to see both deaths of the same system, first a supernova, then a kilonova, would mean catching the full life cycle of a neutron star. From birth to the final clash. That's exactly what happened with the double explosion that rocked astrophysics this year. When scientists began to disassemble the spectrum of its afterglow, the chemical fingerprint of light, something superfluous was found in the data. Something that shouldn't be there. Traces of elements characteristic of a supernova. Traces of the fact that this system survived the explosion, not now, but a long time ago. And when the teams began to reconstruct the history of the system in the opposite direction, the picture was striking. Once upon a time, there were two massive stars in a binary system. Millions of years later, the first one ran out of fuel, exploded, its core became a neutron star. The second survived, continued to burn for millions of years. Then it exploded. Its core also turned into a neutron star. The two monsters circled around each other, and the final countdown began, which ended with what we were watching. From the point of view of physics, this event is an almost impossible coincidence. When a star explodes as a supernova, it loses a huge chunk of its mass, sometimes more than half. The gravitational bond between the two stars weakens dramatically. In most cases, the system simply disintegrates. The neutron star flies into space like an ejected projectile. This is called a kick because of the asymmetry of the explosion. In order for a system to survive after the first explosion, the mass of the stars, the distance, the direction of the explosion, and the asymmetry of the collapse must coincide. Such systems are only a few among billions. But our superkilonova survived not once, but twice. After the first supernova, she survived. After the second, again. Nature threw the die twice with a negligible probability, and the right number fell twice. When scientists began to calculate the likelihood of this, some doubted the data itself. The data did not lie. The universe sometimes allows itself the impossible. Now, what exactly did the James Webb telescope see? It was his data that turned this event from interesting to historical. Webb is a fundamentally new way to look at the universe. Its infrared detectors, cooled to near absolute zero, see through clouds of dust and dissect the chemical composition of objects billions of light-years away with a precision unmatched by any instrument before it. The afterglow spectrum is like a fingerprint. Lon then leaves his line. Cerium is his own. Strontium, barium, gold, platinum, each has its own unique trace. Webb recorded the classic R process spectrum with heavy elements in incredible quantities. But in addition, there were traces in the data indicating that the merger took place in an already enriched environment, saturated with material from the previous supernova explosion. It's like detonating a second bomb right in the cloud from the first. The second explosion occurs in an altered environment, and its products are different from what would occur in pure space. The R process proceeded differently here. More effective. Tougher. The output of heavy elements turned out to be different. This double explosion may have produced more gold than any regular kilonova. And this raises a question that turns the whole picture upside down. Because astrophysics has an old mystery, the problem of the origin of heavy elements. The universe began with hydrogen, helium, and a little bit of lithium. Everything else, carbon, iron, gold, uranium, was synthesized later. In stars, in explosions, in mergers. But when scientists calculate how much gold all known kylons must have produced over the entire existence of the universe, the numbers do not add up. There is more gold than there should be. Much more. Where does the superfluous come from? There are several hypotheses. Could it be that some special type supernovae also produce heavy elements through the R process? Maybe mergers of neutron stars with black holes are more efficient than thought. And now, a new answer option. Superkilons. Systems where the second explosion occurs in an enriched environment and produces elements with increased efficiency. Our space monster is the first observational hint that this scenario is real. That it is happening. That it may be part of the answer to one of the main questions of astrochemistry. Now let's take a look at what happens inside a neutron star. This is one of the greatest unsolved mysteries of physics. Literally. We don't know what's at its center. That's honest scientific fact. The density there is so prohibitive that the equations cease to give an unambiguous answer. Are there neutrons? Or have they already dissolved into quarks? Or is it quark matter, a state that has never existed in an earthly laboratory? Or something even more exotic, strange quark matter, which according to some theories is the most stable state of matter in the universe? This is not just a philosophical question. The equation of state of superdense matter directly affects what happens when two neutron stars merge, the shape of the gravitational wave signal, the amount of matter ejected, and the efficiency of the R process. That is why each such event is an experiment that we cannot conduct in the laboratory. Nature puts it for us. The detailed gravitational wave signal of the double explosion is a clue. Another piece of the answer about what neutron stars are actually made of. Gravitational waves are worth talking about separately because they were the first to bring news of this event. Einstein predicted their existence more than 100 years ago. He said, if massive objects move, They create waves in space-time that propagate at the speed of light. And then he added something that almost killed the whole idea. These waves are so weak that it is almost impossible to detect them. That this requires a tool of such precision that humanity does not have and, perhaps, will never have. Einstein was wrong about never. The LIGO and Virgo detectors are literally the most precise measuring instruments ever created by man. They measure the change in the length of their arms by an amount that is 1,000 times smaller than the size of a proton. They were the first to catch the signal of our superkylon, seconds before the telescopes turned in the right direction. The detectors already knew. A trembling of space-time has already been recorded, coming from a dying system billions of light years away. This is called multi-messenger astronomy, when we see the same event through several channels at once. Gravitational waves, gamma radiation, optical light, Webb's infrared spectrum. Each channel told its own part of the story, and only together did they form a complete picture that we had never seen before. The double explosion did not occur in our galaxy or in a neighboring galaxy, far enough away that the light from it traveled to us for a very long time. And this means that we see this event as it was, not today, but in the deep past. A telescope is a time machine. Every time we look at a distant object, we don't see what it is. We see what was. When this light went on its way, our planet may not have existed yet. Or it was just being formed. And the light flew through billions of light years of emptiness, and flew directly into the mirror of the James Webb telescope. Is it dangerous for us? Distance protects. Gamma-ray bursts that accompany neutron star mergers are indeed deadly, but only if they are aimed directly at you and the distance is small enough. Not here. But in the early history of the Earth, such events may have affected it. There is a hypothesis that some of the mass extinctions in the history of life on our planet were caused by gamma-ray bursts from distant astrophysical catastrophes. Not proven, but not absurd either. A gamma-ray burst that hits the atmosphere can destroy the ozone layer for years. Ultraviolet light will flow unhindered. Life on the surface will suffer. The universe is not a safe place. And the more we learn about such events, the better we understand the environment in which we live. This discovery is not the end of the story. This is its beginning. Now scientists know what to look for. They know the signature of superkylons. They know what the spectrum of an event that occurred in an enriched environment looks like. And now they are looking at archival data from a new angle, because similar events could have been recorded before, just no one knew what exactly they were seeing. This is called retrospective analysis, when a new discovery suddenly explains the mysteries that have been accumulating for years. New tools are being built. The Einstein telescope in Europe and the Cosmic Explorer in the United States are both an order of magnitude more sensitive than existing detectors. They will catch gravitational waves from the depths of the universe, where current detectors cannot reach. In space, LISA is being developed, a laser interferometer with arms of 1,000,000 kilometers, a detector that captures frequencies that earthly installations cannot hear. With the next generation of instruments, the next superkilonova will be caught earlier, in more detail, more accurately. And perhaps we will be able to observe it in real time, from the first gravitational wave signal to the extinction of the last afterglow. Behind every scientific discovery, behind every dataset, behind every article, there is something simpler and more important. The moment when a person, a living creature on a small planet near an ordinary star on the outskirts of an ordinary galaxy, looks at the sky and understands something new. Understands something about the universe, which is billions of years old. A universe that doesn't know we exist, and yet made us possible. From their wreckage, from his dead stars, from the gold of his Kylans. We could not stop this explosion, predict it, or control it. We could only observe, study, understand. And in this sense, it is one of the few things that make us unique. Not the size, not power, and the ability to look at a dying star billions of light years away and understand what's going on, why it matters, and how it relates to the ring on your finger. This is our answer to infinity. Somewhere right now, two neutron monsters are circling each other. Another countdown is underway. Another supernova is waiting in the wings. And when it happens, we will be ready, better prepared than ever. Because this year's double catastrophe has taught us one thing: the universe explodes twice. And we see,